My name is Yaniv, and today I'll be talking with you about UPGRADVISOR, early adopting dependency updates using hybrid program analysis and hardware tracer. This is a joint work with my wonderful collaborators listed on the slide. Modern software development is all about deploying new features fast. For example, Facebook ships new versions for their front end and their mobile apps constantly. Now, one quick way to have new features is take pre-existing libraries, wrap them up, boom, you have a new feature. So in our survey, we found that an average application will use 12 direct dependencies and more than 100 transitive dependencies to do their things. Now, dependencies developers are also updating their software fast and all the time, yet the application developers are not quick to update and take these updates into their applications. In our survey of more than 1,000 projects from GitHub across Python, JavaScript, and Ruby, we found that the average of delay days between the time where the dependency is updated and the uptake of the dependency is growing. So starting from 2019 and all the way up to just the end of 2021, we see that the average is just growing across all the languages. And at the end of our survey, the average across the languages was 400 days. That's more than a year. Now, these things have bad consequences. So bugs are being fixed, security holes are being closed, but they're still affecting the applications. Now, at the ecosystem level, the transitive dependence graph start to disagree. All the components are using different versions. Now, in some cases, you can resolve it by everyone sticking to the older version. This is not good because just we're living in the past. But in other cases, this cannot even be solved, and you just fall into a dependency hell. The components don't agree. So this is just one quick example. Very big project from a very big company. Now, one of the developers who's using this package is saying, hey, I'm in dependency hell. The versions are not agreeing. Please update your dependency so I can be updating the other stuff and moving forward. Now, that was end of 2021. Another developer a few months later, same thing, different dependency, please help update. A few months later, different developers, this is getting out of hand, more requirements are breaking, please help. Now, the Naïve solutions don't work. You cannot just update freely all the time because the APIs change. So this can cause a very noisy runtime crash, such as this one, where the API was changed, required a new argument, application didn't supply it, boom. Or, and this is even worse, it can fail silently. Now, you have an update to the API, you think you're okay, you're just wanting to report a crash, but suddenly you're working as a daemon. That's completely different, probably won't work. Now, integration tests should test this and find these problems, but they're not really covering the interfaces for the dependencies. We saw this in our survey, and there's one more survey that says the same thing, essentially. And at the end, manual inspection is just not feasible. So going back to the last slide, all the developers asked is that we update from version 0.4.3 to 0.4.4. That's a very slight update, right? But actually, it's 23 files, almost 500 changes. And now do that times all the updates, times all the dependencies. It just doesn't work. So to address this problem, we suggest UPGRADVISOR, your upgrade advisor. Given the application, the dependency code, and the updated dependency code, UPGRADVISOR will analyze the update and its correlation to your application, trigger the tracer on your production servers. That's a very limited tracer that only tracks the part that is relevant to this question, and it's very low overhead, and I'll show you how later. And issue the advice. So this can be upgrade safe, great update, feel free. This can be upgrade not safe, something is breaking, don't update before you solve it. Or here is a reduced diff, so this is only the part of the dependency that changed. Take care of that and you can update. Now, we built UPGRADVISOR for Python 3. We evaluated it on 172 dependency updates. Now, these are dependency updates for big projects, top start projects. From GitHub from our survey, we found that in 56% of the cases, the update is safe. You can just update. And in the other cases, the reduced diff we issue is 90% smaller than the overall diff that the dependency introduced. And finally, the average overhead was 3%, and the maximum we saw was 6%. So we had all this information. We sampled a few of these dependencies updates, which were safe, and just submitted them to the relevant projects. And so we sampled 9 updates as a pull request. 7 of these were already merged. We got really cool feedback from the developers. They were really positive, which really helped us and motivated us out to continue this. Now, so how do we do it? Our insight is that what you can reach won't hurt you. So application code is not using all of the dependency. It's using parts of it. Now, when the dependency is updated, so you don't really know if you're using the updated parts or not. And this can be a very big change. So ideally, you can look at all your production environments and just know update, and just know which parts are used and which are not used, and only focus on these. Now, to do this thing in practice, you have a few requirements you need to adhere to. So you want to study the update without updating, because if you're updating and it's crashing, then this kind of defeats the purpose. And you don't want to interrupt the application when it's running and test all these weird instrumented versions. You want to do it just flawlessly. And you want to incur low overhead, because if your overhead is too high, no one will do that in practice. And finally, we think that if we do all of this and you trace it for long enough, this can serve as the closest thing you can have to a ground truth about how the application is using the dependency. So giving that insight, we had a few design ideas for how to do UpGradeVisor. So we will combine static analysis with dynamic analysis to discard and safely discard all the non-reachable changes. So the static analysis will take care of all the never reachable changes and just discard them, and only leave you with the maybe reachable changes that will need to be explored dynamically. So this is already shrinking the overhead. Furthermore, we'll use a hardware-based tracer using modern CPUs and their capability to trace to further lower the overhead and make this thing practical. And another thing we do is we want to make sure everyone can use UpGradeVisor. And when we look at what developers are actually using, so they really love JavaScript and Python. I love Python too. And the big repositories for dependencies are NPM, Python, etc. So we want to address these people. And to do that, we'll design UpGradeVisor to allow dynamic languages and maximize the usability. Unfortunately, this means 2 big challenges. First, dynamic languages usually don't have typing information, so anything having to do with static analysis and specifically reachability becomes more complicated. We had to deal with that. And secondly, the hardware tracing capabilities in the CPU was built for native code, and dynamic languages are usually interpreted. So this doesn't mix, and we'll have to solve that too. So I want to show you a quick example of how UpGradeVisor works in a real-life example. So we have QLib. This is an AI-based platform for investment developed by Microsoft. It's pretty popular. Now, QLib uses HyperOpt as a dependency to allow them to do hyperparameter optimization. Now, we'll build the call graphs for these 2 projects. You see a call graph is in the nodes, you have functions. Edges are connections, calls between functions. So you see the purple nodes are for QLib, and the orange ones are for HyperOpt. And you see the connection here where QLib calls HyperOpt. Now, this is not the entire call graph. It doesn't fit into one slide. And we want to help QLib update HyperOpt. So to do that, we'll explore the next version of HyperOpt. And we see in the diff that a few functions are updated. These are the stars on the slide. Next, we can quickly just discard these 2 stars because they're never reachable from QLib. And we don't care about them at this point. They cannot affect us. And that's good, because one of these changes is kind of annoying. It's how signals are changed between Windows and Unix. I don't want to take care of that unless I really have to. And I'm only left with the functions that are changing. And I only need to trace these and none of the other functions in the dependency or QLib, of course. So walking over the tracer outputs, we see that actually one of these functions is visited, but because of the conditions in the function, the change is not visited. So we can discard this thing too. And one less function to take care of, great. At the end, we started with 72 change functions. 94% in this case were discarded statically. 1 more discarded dynamically, you saw that, only leaving us with 3 functions. So 3 functions is something I could look at. I did, and with the help of my lab mates to collaborate that. And at the end, this is one of the pull requests we submitted. And this was like merged under 5 hours. A few weeks later, it was part of the release. So we were pretty happy about it. Now that you know more about UpGradeVisor, you can understand that we had a few challenges we had to address. So first, we're using these call graphs. They have to be sound. If they're not sound, we're missing something. Now, we wanted to create these sound, meaning that if there is a possibility for one function to call the other one, we want to make sure it's represented in the graph. Moreover, and this is kind of subtle, in some cases you will reach the change, but it will not affect the behavior or the semantics of the application and the dependency. And this is not solvable for the general case, but in some patterns we saw again and again in these updates, we could rule these behaviors out, so we did that. Unfortunately, I don't have time to tell you about these. They're mentioned in the paper. Go and read that. I have time for telling you about the last channel and how we addressed that. So we wanted to design a low overhead selective tracer using hardware-based tracing. So before I tell you why it doesn't work, let's just discuss how it was designed to work to trace native code. So we have some C code compiled into assembly. You want to trace that. So using ARM and Intel modern CPUs, they behave very similarly. Instead of tracing all of the instructions being run, you just trace when there's a possibility of a change. So if the function can jump into one point or another point. So conditional jumps and indirect jumps. The results of these are stored on a buffer. Now that buffer is written directly by the CPU. It's a cyclic write buffer on the RAM. And the results are stored there. We call these the tracing records. And these are also dumped into this so they can be used before they're overridden by the CPU. At the end or in the middle of the execution, you can take the tracing records, take the code, and just recreate the trace. So know what the CPU did. This is pretty cool. You want to do the same thing for interpreted languages such as Python. So Python is also compiled, but it's not compiled into native code. It's compiled into bytecode. And this does not run on the CPU. It runs on a fake CPU, which is the Python interpreter for CPython. And the Python interpreter is just coarsely just a big for loop going over the bytecode and doing what the bytecode is telling you and doing also control. So this scheme does not work. You cannot use the CPU as is to trace this code. So a first solution was suggested by my co-authors in last year's PLDI. So Jay suggested the following thing for Java, but it's the same thing. Let's trace the interpreter as a whole, get all of the tracing records for the interpreter, then we can recreate, know what the interpreter did, take that code and the Python code, and now we know what the Python trace did, which is a very cool solution, but it has one major problem, which is high overhead, because you're tracing so many tracing records, and you might miss them if you're not writing them out too soon. And also, it's just you're writing too many of these tracing records for a few bytecodes, and that's just high overhead. So for UPGRADVISOR, we did something completely different. We wanted to go back to tracing the interpreted code. So only for the selected functions, these stars I showed you before, we will divert the interpreter into a special version of the interpreter, a clone, that has these new jumps in red here. So the jump we'll put them where the jumping happens in terms of the bytecodes. So we jump out to this new table we added to the code, and we jump right back. But we tell the CPU to only trace this special new table. And this gives us essentially a way to cast a bytecode jump. We can also cast other stuff, but bytecode jumps into a native jump that the CPU can see. So it just sees exactly what it needs, one bytecode jump, one event, and that's it. We're back to the minimal amount of data we need to recreate the trace. So given this scheme, we have selective tracing. We have two versions of the interpreter, and we have low overhead because we're tracing just the minimal information we need to do this tracing. So now we can talk a bit about the evaluation. I will show the key points, and the rest are in the paper. So first, we wanted to see, okay, so how useful is this thing? So we had 172 dependency updates, possible dependency updates, and we just tried to make the next update. So we started 172. Just running the static part of UPGRADVISOR, we managed to discard all of the changes statically. And in 98% of the 98 cases, so 56%, and we could just update, which is great. And for the rest, we had to trace the execution. Now, we didn't have access to production servers for all of these updates. And instead, we took a representative group of 5 projects, and we set up a production-like environment for them. So we set up the project. If it needs a database, we set up the database. We go and found the workload that are very specifically adjusted to the project and just ran it And also, we focused on the changes and ran some, as far as we could, try to get to these changes in the dependencies. So these are the 5 projects. You can see the diff in lines of code, the percentage of changes discarded statically and discarded dynamically, and what's left. You see here in 2 cases, the static and the dynamic analysis together allowed us, so these are AutoML and Flare, allowed us to discard all of the changes, which is pretty good. And overall, we found that the dynamic part is really good with shaving off the few extra percentage points we needed to make this viable for a developer to look at, or even remove everything altogether. So now that we know that the dynamic tracer is really important, how high is the overhead? I promised you low overhead, right? So we wanted to do another testing setup. In this case, we used the testing suite of the projects just so it can be replicatable. And for one case in Django, we could play with the amount of CPUs used running these tests. Now, we had a few variations. One of them is the full UPGRADVISOR version, which is targeted, so taking only the functions detected by the static analysis. In the next one, we just traced everything. And another one was simulating the solution I told you about before for tracing the entire interpreter. And just one more version that is totally software, take whatever the CPU is doing, put it in the interpreter. And these are the results. So as you can see, the projects on the x-axis and the overhead compared to vanilla on the y-axis, on average, our 2 configurations greatly outperform the other ones, which is showing the importance of each step we did in this design of UPGRADVISOR's tracer. Moreover, you will see that in the multi-CPU cases, the overhead is really high. This is because a lot of CPUs are running together and they need to push the tracing information, which is causing overhead. So in the paper, we compared to cProfile and CoveragePy, which are the very common tools for Python developers to use. And we also have an Instagram Django performance overhead, which they released, and we just took their workbench, and we saw very similar results in terms of overhead. So to conclude, we presented UPGRADVISOR, a system for reducing developer effort and error risk in adopting dependency updates. If you want to know more, check out our site. There's an artifact too. And if you just want to use it, we have a GitHub app you can install, and then you'll get, not too much, but you'll get just pull requests from our bot that you can use. And with that, thank you, and I can take some questions.